The notion of green function, the name should change. Okay, the green function is even more powerful than you think about. Okay, so let me just start some story from my hero. Okay, the hero is Riemann. Okay, so the Riemann. Okay, in his life, he only write one paper on the fluid mechanics. But it just like he wrote only one paper about Riemann hypothesis. Okay, he's influenced everywhere, and he also only write one paper on differential geometry. It turns out everybody doing the Riemann geometry. Okay, so I'm fine. Okay, to raise him as the only hero. Okay, and also include Green. Okay. So now what did Riemann did? Okay, in the 1860. Okay, he considered this problem, the Riemann problem. Okay. So this is a gas on a tube. Okay, so you put the membranes, it separates. Okay, say now the gas here, the density. Okay, the density is a low minus the velocity equal to 0. Okay, and okay, so this is a problem. Okay, Riemann he studied. Okay, an initial value problem for the compressible Euler equation 1D. Okay, and here P law is a law to the gamma. Okay, and this is a partial differential equation. Okay, but okay, so now in nowadays, okay, this day many people talk about the generalized function. Okay, but now in that time of Riemann, he was so smart. We even do not know this notion of this modern technology. Okay, weak solution, etc. Okay, he simply find because this is a hyperbolic PDE. Okay, he know there's something called the Riemann invariant. Okay, so that means that he find the two algebraic function. Okay, then he can reduce. Okay, he can reduce the partial differential equation to implicit function theory. Okay, so that means so now this Riemann he make it this using his Riemann invariant, because this hyperbolic equation you have characteristic curve. Okay, so that all this Riemann invariant is invariant under the characteristic curve. Okay, so eventually he reduced the solution of the PDE into the implicit function theory. So that means he solved the solution in xt. So in some domain, there's some region like this one. In the space-time, okay, he got here some solution in the shock wave. So x dot equal to s. Okay, so there's some equation with a discontinuity in the space-time. Okay, and now there is some expansion wave pattern. Okay, that this Riemann's solution, and so he did the 2x2. And then in the 1956, okay, Peter Lux, okay, I mean we know he's a big guy, okay, he generalized the Riemann problem, okay, from 2x2 to n by n, okay.
What's the meaning of 2x2? Where's 2 and 2?
This two equation, okay, also it means 2x2, okay. And the Peter Lux is generalized, okay, and then eventually the Russian he invented the Goodenough scheme. Okay, to compute the Riemann solution to develop the nuclear bomb. Okay, maybe the people like it. And later, okay, and then later Grimm. Okay, this is also invention. Okay, he using the solution of Riemann. Okay, actually it's a Peter Lux solution. So that's mean he solved PDE in the very nonlinear way. Okay, so that's using the solution of Riemann problem at the building block. Okay, and then he solved all the solution of hyperbolic equation. Okay, in the general form. Okay, and in the class with the PV solution. Okay, so now and then about what is the PV solution? I mean today I'm using blackboard, so I don't mention what is PV. Okay, and now so now so I just tell you the old story. Okay, and now in the modern day, okay, mathematicians love something fancy, okay, because they know the solution of hyperbolic equation will have a discontinuity, okay. So there's a shock wave. That's the Riemann already know it, But after the Lorentz Schwarz, okay, they don't like the equation, okay, I mean, with discontinuity. So they invent the weak solution, okay. So the form of weak solution is, okay, so now say here, so now you have this is a system of differential equation, okay. So now if a solution is, okay, I mean, is smooth, okay, then it makes sense, okay. But now if you want to accommodate solution with discontinuity, okay, you put the solution in a weak form. So you put, okay, so you test, so you multiply this one and this, okay, so that's, so you sub t, okay, and the plus f of u sub x and the dx dt, okay, equal to 0, and this double integration for all three is a function with a compact support, okay, so this okay, we call, okay, and then this okay, and then this f is in the Schwarz space, okay. So we so this means that so this means you try to rewrite equation in the, okay, so this is equation in the strong form, okay. So now you put it in this, okay, you put it by through integration by parts, okay, from 0 to infinity to r, okay. So now we write the solution in weak form. That means u minus u sub t, okay, and u and the plus and the minus f sub x and f of u equal dx dt equal to 0, okay. So now so later on, okay, instead of look at this equation there, and then now you say, okay, if a function u satisfies this equal to 0 for all test function, then we call this solution is a weak solution, okay. And now they say, okay, the beauty we want to look at the weak solution is that if you write everything in this form, it do not talk, it didn't touch the differentiation in here. So everything is looks good, okay. But however, it only looks good. It don't offer anything, okay, it don't offer anything special, okay. Okay, some French people, they say, okay, the compensate compactness, okay, then take it, you find the weak limit, etc., okay. And now, okay, now I tell you, okay, I mean, what the problem for the quasi-linear problem, okay, because this problem is a quasi-linear, okay. You put the solution in the weak form. It got a problem about the uniqueness. I mean, the well-posedness. What the problem? Okay, I give you some simple example. So now you look, okay. Actually is a Berger equation is everybody's love of everybody's favor. Okay, so now I also use the Berger's equation. Okay, so now if you look here, so now if I look at the Berger equation, this is a quasi-linear equation. Okay, and now if you look at the initial value problem, okay, yesterday only talked about the Herder continuity on the initial data. Okay, and now actually that's true. Non-linear problem is very interesting. Okay, so now if you look here, if I look at initial data like here, x and u, put here u equal to -1, u plus 1. Okay, this is initial data. Okay, so this put t equal to 0. Okay, and now you look here. Okay, so there is x and it's u. This is also a solution or weak solution. Okay, and now I mean the same initial data. If you look at this expansion wave pattern. Okay, so this u and this x for some t. Okay, so so this u, this is for some t, and now here it take this one is u equal to x over t here, and u equal to 1, u equal to -1. Okay, so both are weak solution for the Berger equation. So this means that the initial value problem for the quasi-linear problem is the problem. Okay, so this means this raises the problem of the well-posedness of the quasi-linear equation. Okay, so now I just say some story about for the hyperbolic conservation though, okay, I mean to exclude, okay, so this solution is not good, okay. I mean you need to impose some entropy condition, okay. You will exclude this one, okay. Okay, so now so this is a story of, okay, some background about quasi-linear, okay. So now I just tell you that, okay, for a quasi-linear PDE, okay, the well-posedness is a big headache, okay, because I mean you see have a non-uniqueness, okay. So now, okay, so now I'm living in this century, okay. Riemann he considers for the case of hyperbolic equation. Now I want to tell you, okay, that the similar story, okay, is for the Navier-Stokes equation, okay. I mean, but this now this is not a toy problem. This is a real problem, okay. That the solution of Navier-Stokes equation, which is everybody study it, okay. So now I'm write down the equation here. So now this V is means the volume, okay, volume, and the U is means the velocity. So the first equation is a conservation of mass, okay, in Lagrangian coordinate. And the second equation is a momentum equation. So you write here this U is fluid velocity, okay, and now P is pressure, and X, okay, now here is the viscosity U sub X over V over X, okay. So now here this P of V is equal to V to the minus gamma, okay. And now I tell you that, okay, this is new discovery, okay. Everybody look at the Navier-Stokes equation, okay. But now, okay, I mean about the well-posedness, okay. I need to impose gamma is between 1 and e exponential, okay. This is some new invention, okay. In order to have a construct solution. So yesterday talk about, okay, constructor of a non-solution operator. So today I will tell you something is that the construction of solution operator without thinking about refer to the functional space. Okay, now I'm telling you that today the approach is a completely different thing. Okay, I mean, okay. So now I tell you what the problem of this. So now if you consider this problem like a shock tube problem, okay. So this means that so you know, okay, I mean if the shock tube problem, the solution will have discontinuity. And now look here. So now if you allow here, this is second derivative, okay? And now if you have a V discontinuity, okay, you got a headache. Because this you think like this heat equation, okay? And now your coefficient not in any C, okay? Even the George estimate don't work on this situation, okay? I mean you have this discontinuity in your coefficient of the viscosity. So this is very trouble, okay? And now, okay, this problem has been studied by many people before, okay? And then there's many progress, like, okay, I mean, you can say like Nash, okay, and then many Japanese, Italia, Russia, Canal, and Cisco, okay, and many people work here, and include Pierre Leon, David Hall, okay. And now, okay, yesterday many people talk about renormalization there, okay. So, and also sometimes a cut off here. And now in terms of PDE, okay, what they mean in renormalization? So okay, so people still want to study this problem. What they did? They make an assumption on initial data. Okay, so usually people say here, okay, so in order to have all classical theory of functional analysis, okay, let's assume initial data is like if 3 dimension they require an H3, okay, so then everybody is starting with this Sobolev, okay, so I might say, okay, Sobolev something, okay, but that's good, but it's not that good, okay, so you need to think something else, okay, because see here, if this one has this continuity there, it's not in the, even not in the, okay, it's only on the L2, okay, but L2 is bad space, because L2 do not allow delta function, etc. Okay, so that so now you need, so you will face some many trouble. Okay, so now, okay, I was born in the time of functional analysis. Okay, but I I will be solved quite a little bit. Okay, functional analysis is good, but not that good. You need to think something else. Okay, now okay, so now we go back to 1860. How Riemann, if I were Riemann, okay, if Riemann were me, how you will think this problem. Okay, so now, so now I will say, okay, so now, so now we think, okay, so now I just tell you, okay, what is a connection? Okay, so now Riemann he did, okay, he first what is the non-linearity? Okay, so now, okay, so now I just give a very small lesson, okay, like I'm teaching the PDE. Though my teaching ability is very bad in Singapore, but I still love to say, okay, we need that. Okay, I tell you, okay, what is the connection of the Riemann to all these problems? Okay, so now see here. If okay, so now you teach students how to solve this problem. Okay, so now you look at the space-time. Okay, so now you look in the space-time, x and the t. Okay, so we put here, say here I have point in the space-time here. Okay, so what you do here? Okay, we will do say we tell student, oh look here, we have a solution here. We put u. Okay, so put u is the solution at this point here, and it draw a straight line back. Okay, and we call it the characteristic curve. So dx dt is equal to u. Okay, and then now suppose here this is your initial data, ux0 is equal to u not x. Okay, so now Riemann will say, okay, so the solution is a Riemann as a constant at this point. So this means your solution u at this point is the same value here. And now this y will take it as initial data. Okay, now if this x here, so the displacement, so this t, so this one is a distance u of t. So this position is okay, is x go back ut. Okay, so then, so this means the value here is the same here. So now here this means x minus ut. Okay, so now this is implicit function theory. Okay, so now, okay, because the dependence of u is here and here. Okay, and this u not here. Okay, so then you convert a differential equation to the implicit function theory. Okay, so now, okay, so now I'm just telling you here. So how I'm going to make a connection from the Riemann's way to this problem. Okay, so now let's look here. Question. Okay, so now the thing here. So first, Riemann, okay, leave the position here. Okay, so now he leave u is some indeterminate thing here. Okay, and now, okay, question. What do you mean characteristic curve? Okay, so now characteristic curve is means a delta function. Okay, this is y minus x minus u t minus tau. Okay, so now if you put the measure of delta function here, so that's mean that the meaning of u, the meaning you mean the characteristic curve is mean the delta function. This y, and this y is actually is what it mean. It's a Green function of the hyperbolic equation. Okay, so now, so the notion, okay, the notion of the characteristic curve, you can think this one is a Green function of the hyperbolic equation here, and put the a, okay, we put this one as a parameter inside your delta function. Okay, your Green function. Okay, so now here, so okay, so now I just say here, okay, so so all the ingredients what you need here is that, okay, the space-time position here, put the solution as a parameter into the Green's function, okay, for linear, okay, this okay, so this characteristic curve here is a linear, is a Green function of a linear hyperbolic equation. Okay, so now, okay, so I want to imitate how would Riemann do this problem. Okay, so now, okay, so now okay, it's too bad, I erased this line. Okay, so now I go back to this picture now. Okay, so now say here, is a given position there. Okay. So now we put this equation in the form. Okay. So they put the ut. Okay. I mean, it's, okay. So now, if frozen the equation here, so you have a ut minus beta square, this v sub x. Okay. So now this is local sound speed. Okay. So here you write this one. This is beta sound speed here. And now this one, you put this one is this one is alpha. Okay, this is uxx. Okay. So now it's okay. So now, if you frozen your position at the given point, just like you say, the light cone. Okay. So now here for the hyperbolic equation, at each given point, it has its own light cone of this one. But here, this you have its own dissipation. Okay. So now I would say, okay, so now I would imitate how would Riemann do it, okay? So now if I look here at the position there, okay, so I look at my local information. I have my local sound speed. I have my local, okay, viscosity, okay? So now I put everything like in the way, like a quantum field or whatever. So that means at each given space point here, you can have a family of symbols, or you would like to say here. So now here, so now you look here, so now at each given point here, you relate it to sound speed or and the viscosity. Okay, so that means like you like you mean you like cone. Okay, so now I just pretend here at each point here. Okay, so I assign a symbol. Okay, so here is a minus I8. Okay, minus I eta. Okay, and the minus beta eta I eta. Okay, and now here alpha beta square. Okay, so here put here to the okay, so like this one. Okay, so now this is like you look at if people do a pseudo differential operator, they prefer like this one. Okay, like when solving the equation of a variable coefficient, at each point you assign a symbol, right? Okay, so that means. So so the light cone, okay, if you assign light cone, assign something like this one in Fourier space as Fourier symbol here. This is I eta, okay. But now, okay, so now I just look like people in order here. Okay, so now at the frozen state, okay, I assign a symbol, okay. Now let's think here, what do you mean a symbol? Okay, symbol you can write down as a semi-group, right? I mean, okay, so that means like at each given point there, you assign a symbol. Okay, so a symbol, okay, the same, you assign a semi-group. Okay, now, okay, now at this moment I will tell you here. Okay, so now usually we will say, okay, everybody want to cut out singularity or etc. etc. Okay, you think enemy. Okay, you always think singularity is your enemy. Okay, now I'm saying here, singularity is your friend. To reduce non-linearity, okay. Okay, so now here we come into okay. So now I don't do any edge soft stuff, okay, for non-linear problem. So now your main tool is singularity, okay. Okay, you need to realize, okay, you need to have understand what is a singularity, okay, before you go ahead. So the reason make me different from all the other people in the other field, okay. I'm not afraid to say such thing anymore, okay. Now, okay, so now I'm going to tell you here, so what does this mean? Okay, so, okay, now, okay, I also have, agenda, okay. Fourier, okay, high frequency is good only for linear problem, okay. For nonlinear problem, high frequency is a disaster, okay. So I will say here, okay, nonlinear, okay, so the reason, okay, now let's say here, the way of pseudo differential operator is good, okay, for linear problem, because linear, okay, the Fourier space, okay, it can commute with the nonlinearity, but in the but for the nonlinear problem, the pseudo differential operator never so good if you face the real nonlinear problem, because they do not commute, okay. If you commute the nonlinear term with some operator, it don't generate good thing here, okay. So now, but however, now I tell you there, Green function in the space-time is good, okay. So now regarding to this symbol, okay. So now if you take, so now for the each symbol, okay, if you look into, okay, if you apply the inverse Fourier transform, okay, then you will define a green function, okay, I mean here, this x and the t. So now I put this alpha beta, okay, as a parameter, okay. So regarding to this symbol, you have a green function, okay. Now, I will tell you here, all this story is important now, okay, because this green function, it has its own space-time structure, okay. So now you you will serve a very good tool, okay. But now if you compute, okay, so now if you just simply using green function, no good, okay, because if you look it into its structure, okay, it's impossible to compute, okay. So now I introduce a new notion here, okay. I write the green function into two parts, the singular part and the regular part, okay. So now listen, most of people might like, okay, cut singularity, etc., okay. So now I'll tell you, and then now that's why I tell you, singularity is a good friend. The only thing, okay, so like Li Dong, you talk about the high frequency wave, low frequency wave there, okay. So now I just tell you here, so now here, how you will see, okay, you want to understand problem without sacrifice it here, okay. So now you go back here. If you do the spectral analysis, you can find the frequency, okay. So now you can find this one is so you will write down as a semi-group here. So you have its eigenvalue, okay, all this spectrum. So now if we write this matrix here, you can find out its eigenvalue in terms of eta, okay. Now now this new approach, okay. So so now how I will refer the singularity, okay. So now this one you take, okay, so now you expand the spectrum at the infinity, okay. So now you can expand the spectrum at the infinity, okay. So you can, okay, so now here this one is 2 by 2. You have a two spectrum here, okay. So now you can write down the spectrum star eta, okay. So now, and you have a spectrum star eta, okay. So now here, this beauty that you find a asymptotic expansion of the spectrum and at the infinity, and now this one is an analytic function on the real around a stripe of image axis, okay. So now you find an analytic function along the stripe of the real axis, okay, and then so now you can write here, so it becomes like people doing quantum mechanics, they love this one. So you can put here like this one, eta, okay. So now put here to the some power, say k, very big, okay. So now here is alpha, okay. Put alpha very big, okay. So now you replace the original spectrum here at the infinity, okay, up to say here up to 6 or 7 here, okay. And now what the problem here, okay. And now if, okay, now I just tell you, okay, some calculation, okay, so I mean just write down here, okay. So you'll find out that the spectrum, so now you write down the first one, okay, so you will find out here is a minus beta square over alpha, okay. Okay, so here, so this one have a spectrum is expansion at infinity like this one, okay. And now here you have something, another one is a minus alpha eta square like this one, okay. Now listen, in here,
how do you have some expression for the solution in terms of a green function?
Solution in terms of green function, not yet, so you don't need a green function, okay. If you think the green function is mistake, okay. Okay. So now, okay, so now I'm going to tell you here how you, okay, starting from the linear PD, okay. So now I'm saying here you need to think linear PD differently, okay. And now let's tell you, okay, so now here you have a symbol, right? Okay, and they compute the symbol of the eigenvalue, okay, the spectrum of the symbol here, okay. Then now, okay, now I tell you here, you expand the symbol at infinity, not the origin. Okay, people always do it at origin. Okay, so you do that at infinity. Okay, and now look here. There, this one is a symbol at the infinity of this one. So now this look here. If we look at exponential, okay, so here the symbol of this one at the infinity. This one, this symbol do not. Okay, so that means this function is the Fourier space do not decay at the infinity. So this means this is a delta function, singularity here. Okay, and now this one more or less like a heat dissipation. Okay, so now here is the first time you understand. Okay, the spectral property here is two things: the singularity here and the spectral. Okay, so now okay, you use this spectral infinity. Okay, you rewrite the green function as a two part. The singular part. Okay, so this singular part have a two part. Okay, like this one, and now and the sharp. Okay, now I tell you here. The nature of fluid mechanics we observe is due to the regular light part. Okay, so this is low frequency wave. You see all this sound wave, all this one is due to the low frequency wave show up here. Okay, so this is global structure. Okay, and now all this to handle all this singularity in this one here is due to this. Okay, so now here is the two parts of singularity. Okay, one part is just like delta function. It's a it get along. It's a propagate here. Okay, so now so you got so now I tell you why all this mathematical analysis of Navier-Stokes equation gets so massive. Because you don't understand the structure of singularity. You just want to use one machinery to understand everything here. Then it goes, of course, it go nowhere, because some like people in here, some people go left, some people go the right. Okay, but you want to them to both together? No. Okay, there always some people against each other. So now the thing here, you need to distinguish. Okay. The singular structure among the singularity here, there are two parts. There are two types. One is remain like a delta function all the time. Okay, and the someone will gain regularity. It's like a dissipation spread out. Okay, so now you need to separate them. Okay, so now you got this one here. Okay, and now this is not the end of story. Okay, so now I'm just telling you how you're going to use all this information to digest this problem. Okay, so first you need to have this kind of structure. Okay, now this is really got things interesting here. Okay, so now so now I'm telling you here there is some singular structure here. It's okay. So now so now if I write this part, this singular part, okay, you have this property G star 1, okay, X T, okay, here alpha beta, okay, it have this property. Okay, so now if I take a derivative here, okay, then you have delta function here, delta prime x here. Okay, so e to the minus minus beta square over t alpha t here. Okay, and the plus delta function. Okay, now they tell you here, okay, that in particular okay, that's okay, that you need to realize, okay, all the structure, how it related to non-linearity. So in here, you take you have delta function here, but delta function, it do not show up on every position. You only have this 1, 1, 0, 0, okay? And okay, and the second one here, the structure, the delta function show up on this 1 and the beta square and the here, and the rest is the regular part. Okay, okay. Now, okay. So now I address this point here. This is a key. Okay, let delta function is show up on this one here. Okay, and now this one here. Okay, so now And now we go back to this. Okay, now we go back to here. The non-linearity is on this part. Okay, so I will tell you. Okay, how this non-linearity orthogonal to this structure. Okay, this is important. Okay, so now, okay, now we go back here. Okay, I'm going to tell you how to do the reduction through the structure of singularity here. Okay, so now. Okay, so now the next right here is a kind of different way. Okay, so now we go. Okay, so now if I write this equation, okay, so now if I put this one is in the form like the ut. Okay, sorry, I put it as a v as the w tau. Okay, I write this equation in the vector form. Okay, so I write this one in like here is f of w. Okay, so I put now a change to the y variable. Okay, so now this is the equation there. Okay, so now I say here I starting from the weak solution, right? Okay, so now I put this one. So now this is the equation there. So now, okay, you use the test function, right? So now the dy d tau equal to 0. Okay, and now that's the first thing I in the very beginning I criticize test function is just like people in the UST they told me it's a mathematical nonsense. Okay, so now I'm going to tell you. Okay, actually it's a mathematically interesting. Okay, so now the notion here of the test function what I'm going to do here. So now let's see here. So now if I look in the space time here. Okay, so as I say here, so as given xt here. Okay, so I have a frozen. Okay, I have frozen sound speed. Okay, and frozen viscosity and the sound speed here. Okay, so now I use the information, the sound speed and the viscosity. So now I take my test function and the g star 1. Okay, so now g star 1. Okay, so now here I have a parameter here. I define the each given point there is a field of Green's function or variable. Okay, so now I use this g as my test function. Okay, so now here take the x minus y t minus tau alpha bar beta bar. Okay, so now we use this structured test function to represent the solution. Then what you get? Okay, so now everybody now. Okay, so now what we do now is integration by parts. Okay, so you will see. Okay, so then you will see here the w. So you will get the w. Okay, so here. Okay, multiply with g star 1. Okay, so here you take a dy. Okay, so this one take the time. Okay, because integration by parts. Okay, you get this one, and we got this boundary term here. Okay, and now for these two terms here, you do integration by parts. Okay, so okay, I mean because now you frozen. So now this one is frozen. So you will truncate out all the linear term, only the okay. So then what you will get here? So you get a representation here. So that this one is time equal to tau equal to 0. Okay, this is like the wave propagator here. And now if minus the nonlinear. So here you have this nonlinear term here. So this is g star 1 and then sub y minus x minus y t minus tau, and now this f and the w subtract so now as your background there. Okay, so now if I say this background is u na. Okay, so now you're frozen. There are u na, and now f prime. This is u na. Okay, so here the w minus w na. Okay, so this one is not so bad. Okay, I mean this because you take out something there. Okay, now hyperbolic part here. Okay, now we handle. Okay, so now you still one extra term here is equal to minus this one, this okay. So now I perform integration by part here. So this one you have this is the p, this w minus okay. So this w is u na okay, and here this is y dy d tau okay. So now here you got the representation of the solution okay in terms of okay initial data okay this one information from the initial data okay. So this one make a connection from initial data to the solution at a given point here. So now and now here you have extra contribution from the nonlinear term okay. So now I just tell you here all the trouble is due to this quasi-linear nonlinear term okay. So now let's compute okay. So I say here I have G here okay. So now okay. So I'm going to look into this picture here. Okay. So now you okay. So now you write down okay. So now let me just write down this may okay. Say here I have w, y okay. So now my nonlinear term okay. Let's just write down our nonlinear term here. So here is a nonlinear term is okay. This the first column conservation. No, you don't have a component here okay. And now here you have u sub y, and then now this v okay. And now subtract the fluctuation u okay. So here okay I take kappa equal to what okay. So now here you have this sin here okay. So you okay. So all the nonlinear term is of this one here okay. So now this one is there okay. How are we going to okay? This one is okay. So this one is nonlinearity okay. So now look here okay. So here I have okay. So here I have okay. I have this okay. So I plus this term here okay. So now look here your green form okay. So now here this one is take a derivative here. There delta function delta prime here right. So delta prime will show up under this component okay. So now you look here, this component and this component are orthogonal okay. So now look here. So this means that the structure of nonlinearity you eliminate this one okay. So you the first here you observe your nonlinearity is orthogonal to the first of all the singularity okay. And now okay you still have okay. You still have one singularity and this one is a beta here okay. So now so this means and now here this double integration here okay. So you have a delta function. The delta function okay. You make your line double integral into line integral okay. So then this one here okay. So now let's write down here the first okay this component here. So now this one here it converts the information on the velocity field into the density field. So then you get this one. You only time integral here okay. So this one is a beta. You have this so here you get this one is a 0 okay. And now here is you have this beta okay. Now remember this beta is the information from your green function. This is constant okay. This is beta. So you get it. So you get here is beta okay. And now here u sub y over v minus u sub y v bar okay. So now you get here okay. And the rest is the integral term here. Now okay. So now how you do now okay. So now first okay I take the singularity to reduce double integral into line integral okay. This first thing here. The next one here okay. This one is a v and u. They're function of two variables right. But now look here the Navier-Stokes equation the first equation is v sub t minus u sub y equal to 0 okay. So now at this point you can swap space and time okay. So now here this derivative in the space derivative here you can switch into the time derivative okay, you swap space and time, okay. So now the space derivative become time derivative. So now this means you switch the space-time rule in here, and now look here, your integration is over the time, okay. So then you can integrate out this one, okay. Now this is here, singularity help you, okay, to swap the non-linearity, okay. This is a two variable, right? Now you switch into what? Only one variable, and you integrate out, okay. So this means your non-linear term it just becomes what? A function of v, okay, and they show up only on the time variance, okay. So okay, so now okay, since my time is way over, okay, so I just tell you there. So now with this one here, okay, so then I reduce, okay, I reduce this quasi-linear PDE into a zeroth order representation. Okay, now look here. So now see, so now this delta function is already gone, right? Okay, and now the rest of the thing here is the regular part, right? The rest is the regular part. Okay, so then the regular part is just push into the green function there, it become a integrable operator. So eventually you will get the represent. Okay, so eventually what you will get here. Okay. Okay. So eventually, you will get the representation. You write down your Vxt, okay, is equal to some functional, okay. You get some functional, okay, and it depends on what, okay. This functional depends on, okay, I mean the input V, okay, and the input of the, okay, here is the initial data U now, okay. V now, U now. Okay, so now eventually you reduce the equation into the, okay. So now eventually you reduce this system of PDE into a scalar equation. Okay. And now in here the dependence here only zeroth order. Okay. And then okay, I need the property. I need to make the assumption here the gamma, the pressure constant is less than E. To observe this one would be a contraction map. Okay, and now I tell you one more thing there. When I construct there, I do not make any assumption on the initial data. Okay, so now I can allow my initial data as weak as I want. Okay, so I put the PV now. Okay, so now this make a big distinction. Okay, everybody always start from, okay, let's start from the Sobolev space, Basel space, whatever. No, okay. You just starting from, say here, whatever, this is a PV. Okay, whatever is, okay, you can allow this a major. Okay, whatever. As long as, okay, because now, the way I define this F, okay, is not from anything else. It's just from the symbol. Okay. So that on this part, okay, I have a control of the regular part and the singular part of this symbol. So now I frozen all this coefficient here to develop a machinery. Okay, so then I develop this nonlinear function. Okay, so with this functional, okay, I can prove there is problem. Okay, so now you might ask me, okay, so okay, now your problem is 1D. Okay, okay, but as I tell you, okay, essentially if you look at the structure of the position of the singularity, it doesn't matter. Essentially, okay, the singularity will follow the fluid velocity, the particle path. Okay, so this means it doesn't matter it's a multi-D or 1D. But anyway, I need time to work it out. Okay, and the one more thing here. Okay, I tell here my observation here. Okay, so that means here this is system of equation there. Okay, so eventually I reduce into the equation only on pressure term, only on the density. So this means what? Okay, so from here, okay. So that means you can compute the velocity field through the pressure. Okay, so this means that so this makes sense when you do the weather prediction. Okay, the motion of wind is due to the pressure difference. Okay, so in this observation here, okay, that whatever you want to do here, you just need to accommodate how is the distribution here, and the dependence. Okay, dependence of velocity only from the initial data. So this give me, okay, many things all now start make sense. Okay, so that means all this here, the important thing is to compute density. So now density corresponding to pressure. Okay, so now I just feel okay. With all this new structure. Okay, so that means it's okay. So that means you started something like a test function. Okay. But you replace your test function by all these structured symbol, okay? And all these structured symbol, it turns out it's a very strong singular structure. So now you use all these singular structure to decompose nonlinearity, okay? So now this is the, okay, I think, okay, this is the only, okay, this may be only 3 work. One by Riemann, okay, solving the problem purely nonlinear. And the other is James Green. Okay, he uses the solution of the Riemann problem to solve the hyperbolic equation. And now this one is another example solving nonlinear. Okay, solving the PDE from nonlinearity directly. Okay, so I think, okay, so now you might ask me, is any nonlinear problem can do this well? My answer would be no. Okay, the reason here, okay, that just like a 2-number series, okay, all the not necessary every number is prime number, okay. So they only have some specific question. You have this nice structure. So I believe, okay, I mean, the Navier-Stokes equation is a God-given problem. Okay, it should have a such nice structure. That become like a religion. Okay, I mean, if you deal with a God-given problem, okay, there should be have some proper way to handle it, not just this abstract, okay, I mean, approach. Okay, it won't solve anything.